In this video I want to show you how the MEN system works. Generally an MEN system includes a domestic switchboard, a supply. In this video we'll switch out the main neutral in open position. We'll have a good position, and we'll also have a high resistance neutral. We have representation of earth equipment in the installation. We've got the customer's main switchboard, the earth electrode, the water pipe, and an independent earth. This independent earth is vital because, and this is a representation of what will be used out in the field, it's vital because we don't want to interfere with the earthing system that's faulty. Therefore the independent earth comes into play. The first scenario will reenact what a good installation should be. We have the switch set in a good neutral, a compliant neutral. We have our supply there. We take a measurement, and we're using extra low voltage, but the representation will tell us we have 24 volts or thereabouts. Okay. We'll be using the independent earth, and the first procedure is to turn the main switch on and the first circuit breaker, the wall oven. Now, we start with the supply, incoming supply, 24 volts. And then we use our independent earth, and we test then the water pipe, or the earthing system of the water pipe, and the actual frame of the wall oven. And in both cases there are 0 volts on those 2 points. Then we test the supply at the wall oven, which should be 24 volts. Now, as we turn load on, there should be no fluctuation in voltages or on the earthing system. We can see now that there are 0 volts on the water pipe and also a hot plate. So both sets of equipment have 0 volts. We have 24 volts across the hot plate. Okay, and as we turn more load on, changes there should be no changes at all. Okay. This represents a good installation, meaning that the main neutral coming in from the street or from the pit is large. There is a very low resistance, very low impedance. Therefore, return current is returning back to the source, to the start point of the transformer, as it should. And we're not having any voltages in the earthing system. There may be 1 or 2 volts, which is well below the maximum voltage we require. We always have some voltage because there is never a perfect main neutral. Now we'll turn everything off, and we'll go to a scenario where we have a high resistance main neutral. Where that could be is at the mains box, perhaps, a loose connection, an inferior service line, even a poor connection in the street can cause a problem for us. So if we change it now to a high resistance setting number 1, we then put one circuit on. Before we do that, we'll let you know there's 24 volts still there at the supply. Turn circuit 1 on, and we test from independent earth to the water pipe, and we have a register of 4.4 volts. Yeah. Now, if we go to the earth frame of the wall oven, we have same voltage because both points are connected to the earth bar or the earth system. Now, if we test across the wall oven, we have approximately 24 volts, which is the remainder of the 24 volts supply. So 20 volts already tells us there's a problem. We have lower voltage across the terminals of an appliance, and we're now getting a higher voltage on the earthing system, which could potentially become much more dangerous. Now, as we put loads on, we're actually dropping the resistance of the overall installation load. Therefore, the voltage drop increases on the earthing system and decreases again on the across the loads. You'll see here the voltage on the earthing system is up to 7.6 volts, and the same will be evident on the appliance hot plate, frame of the hot plate, and the frame of the wall oven. And across the actual hot plate, the load, we're at 17 volts, which could represent quite a voltage drop, you know, in an external situation, in a live situation. The worst scenario in this high resistance area is when all loads are put on, yeah? So you'll see now that we have a voltage of around 10 volts on the earthing system, yeah? So 10 volts are recorded from independent earth to the earth frame of equipment, and you'll see now across the load is 14.7, which could be extremely dangerous. Now, if you're in a normal situation in a house and we put a lot of lights on, you'll see they'll be dimming because that voltage drop across the load has been reduced, and therefore an increased voltage drop across on the earthing system. Overall, the voltage on the earthing system and across the load have to represent a total voltage at the installation. So the last scenario is the worst scenario, where we have a total open circuit neutral, where we don't have a neutral at the mains box, broken neutral at the in the pit, or the service line is totally broken. So if we go now to open circuit neutral, I'll turn these off, and we now test the supply coming in. Still we have our normal supply into the installation. Yeah. So now independent earth to the water pipe, we're getting 7.5 volts. And we've got the frame of the wall oven, 7.5 volts. Supply across the wall oven is 17 volts. Now, this is only one load. As we put more load on, we're going to increase the voltage across on the earthing system, decrease across the load, becoming much more dangerous. So put more load on, you'll see now the voltage on the earthing system is up to 11.7 volts, yeah, to the frame wall oven and hot plate. And now you'll see across the load we have 12.13 volts, 13 volts. Okay, one more, the last scenario where we have a lot of load in the house, and we now have a very bad system. We have 14.2 volts on the water pipe, and onto the frame 14.2, and that's virtually half of what you're going to get across the loads, yeah? Nearly half, 10.4. This makes equipment in the house redundant. It doesn't work. It needs 230. It could be getting 160, 170 volts. They're the three situations that could happen. Thank you.